Well, greetings everybody. Here's where we stand with this problem at the moment. I made an introduction video where I didn't really do any math. I just tried to explain the concept of what's happening here. And then I did part A. I showed you how the math works out, how we use calculus. Now I'd like to do part B, and I'll get right into it. So we have this situation of the ladder leaning against the wall, and it forms a triangle with this side fixed at 25 and these sides changing because the base of the ladder is sliding this way, and the triangle formed by the base and the top of the ladder and the contact points with the wall and the floor make a triangle, a right triangle to be specific. Okay, so I've got all that, and in this problem, part B, it says how fast is the area of the triangle changing as this side gets bigger and this side gets smaller. So I say it like that because if the base of the ladder slides that way, then the base of this triangle, this aspect, x, gets bigger, but as a result, this aspect, y, gets smaller. This side stays fixed because that's how big the ladder is. Okay, so I might interpret it this way. For part B, I know that dx over dt is 7 feet per second, and I know that x, the moment I'm interested in, is 24 feet. Okay, so at the moment I want to solve this problem and answer this question about how fast the area is changing, the base of the ladder at that moment is 24 feet. So that's what I'm given. I also, just in case, part A, I found out that dy over dt is negative 24 feet per second. Okay, this side's getting bigger by 7 feet per second. This side's getting smaller by 24 feet per second. So I might need that. It's in part A. Okay, and with all that, I want to know what the derivative dA over dt is, and that would have units of square feet per second. Okay, so dA over dt, yes, that's how I'm interpreting in terms of calculus the change in area per unit in time. Okay, that's the derivative that indicates my answer to part B. So when I do my work, I'll expect dA over dt to show up, and that's what I'm trying to ultimately figure out. Given that I have other things, I have dx over dt, I have x is 24, I have dy over dt, and so on. So let me remind you about the procedure I gave you. It says, 1, start with a true equation that relates the variables of interest. Okay, so I have x and y, I have information about those, and then I want something about how the area is changing. So I need an equation that relates for this triangle x and y and the area of that triangle. So that would be this. This is just a true equation. It's that area is 1/2 base times height for that triangle. That gives us something to work with. That's our starting point. That's the true equation for the situation that relates the variables of interest, which in this case are x and y and area. Okay? Now, once you have that, take the derivative with respect to time of that equation, everything you see there, using applicable rules. So I have to take the derivative with respect to time of the equation. Area is 1/2 xy. Okay, so I need to use the rules as they apply. So for the derivative with respect to t of a, that would be 1, the derivative of a, like just a to the first power, times dA over dt. Now in the video I just made, I said the reason we multiply by dA over dt is like the chain rule. Okay, that a area there is not just some variable unrelated to other aspects in this problem. It is a function of time. That's why I have to say the derivative with respect to t time of a is 1 times d over dt. On the other side, I can carry down this half, but using applicable rules for derivatives, x times y is the product of two functions. So I'd have to use the product rule. So here goes. The derivative of x times y is the derivative of x times y plus the derivative of y times x by the product rule. In this case, for this kind of problem, that translates to dx over dt times y plus dy over dt times x. And there, in that part, that concludes step 2. The calculus is over at this point. For me to take the derivative with respect to time with whatever rules are applicable is all the calculus that's involved in this. The rest of this would be algebra or geometry or something like that. So when I go to step 3 and I solve this equation that I got here in 2 for the unknown derivative that I want, and I'm sure to use all known information at that point, then that's all that's left. Okay, so let's see. Here we are. We have this. Okay, how would I begin to use all known information? Like, do I know dx over dt? Do I know y? Do I know dy over dt? Do I know any of this stuff? Because if I know it, I'll have to use it in this equation. Okay, notice unless I know what these other things are, I can't tell you what dA over dt is, because there's all these other unknowns over here. So do I know some of that? So I would say to that, yes. Okay, I know that dx over dt is 7, so say I put that in right there. I know that dy over dt is negative 24, so I put that in also. So I know those derivatives. Do I know x and y? Okay, well, one condition on my problem was that x was 24 feet. So I know that x is 24, so I put that in. But do I know y? Well, when I did part A of this problem, I said, well, yeah, if you know x, you know y. Like, so we got this triangle, this side's 25. You tell me this side's 24. I can tell you that side. I can tell you the y. By the Pythagorean theorem, solve it, I get y is 7 if x turns out to be 24. So y is 7, x 24, dx dt is 7, dy over dt is negative 24. Okay, so then I've used everything that I have, and that turns out to be enough for me to figure out what dA over dt is, which is ultimately the answer to how fast the area is changing in this triangle. Okay, so do a little math there. 7 times 7 minus 24 times 24 is negative 527 times a half is negative 263.5 units. Area over time, square feet per second. Okay, so because that's negative, I would interpret it like this. The area is getting smaller. And that's no surprise. See this triangle? If this side gets bigger and this side stays fixed, then the area has got to be squeezed out. Okay, can you imagine that? So yes, it's negative. It's getting smaller. That's what that means. Getting smaller by 263.5 square feet for every second. Okay, so that's how you solve it. I hope you see how that matches up to my initial procedure. Okay, now one more thing. I want to make sure that as, like, say I went from here to here, that you understand the differences between the x and the y, the dx dt and the dy dt. What's the difference between all those things? Well, x and y are just distances. Like, the base of the triangle is 24 feet. As a result, the height of the triangle is 7 feet. X and y are just distances. But the dx over dt and the dy over dt, those are how the distances are changing. Those are derivatives. So for that information, I wouldn't look for something that's in feet. I would look for something that's in feet per second. So if we were like going to go back here and I'd say, what's what? Like, is that 24? Is that dx over dt, or is that an x? Well, that's a static measurement. It's 24 feet. It's a distance. It's how the length of that base of the triangle is 24 feet. That's what that is. That's just x. But this other number, 7 feet per second, that is how the distances are changing. Oh, feet per second. That is how fast they're changing. See? Feet versus feet per second. So that number, I would say, okay, I recognize that's a derivative. So we don't want to get those confused. And I don't want to take that for granted. So make sure that you pay attention to the units in the problem, and that you can tell, you know, for information that you incorporate later, what's just a variable like x and what's a derivative like dx over dt. Same thing applies for y and dy over dt. One of those is a distance, and the other is how fast the distance is changing.